Yes, the calculations are correct. Using a wireway requires larger conductors for the same ampacity compared to individual conduits due to temperature derating. In a wireway, multiple conductors are bundled together, resulting in higher operating temperatures. To prevent overheating, conductors must be derated, which means reduced in ampacity to account for this elevated temperature. The ambient temperature, which is 30 degrees Celsius in this case, also affects the ampacity of the conductors. Higher ambient temperatures require further derating to prevent conductors from exceeding their temperature limits. The 20% fill rule for wireways is based on the cross-sectional area of the wireway. This means that even if the bundle of conductors occupies less than 20% of the area, the derating factors must be applied. In individual conduits, the conductors are spaced apart, allowing for better heat dissipation. This results in lower operating temperatures and less need for derating. As a result, smaller conductors can be used in individual conduits compared to wireways for the same ampacity. The larger conductor sizes required for wireways can increase the overall cost of the installation. It can also make it more difficult to route and install the conductors in the wireway. However, wireways still offer advantages such as flexibility, ease of access, and improved aesthetics. To minimize the conductor size and cost, consider firstly optimizing the wireway layout to minimize conductor bundle length. Secondly, using conductors with high temperature ratings, for example, THHN-90 degrees Celsius instead of THHN-75 degrees Celsius. And thirdly, providing additional ventilation or cooling to reduce operating temperatures. Let's delve into the specifics of ampacity derating in wireways and compare it to individual conduits. We'll begin with a detailed look at temperature derating. When multiple current-carrying conductors are installed within a wireway, they generate heat. Since the wireway is typically an enclosed space, this heat becomes trapped, causing the overall temperature inside the wireway to rise. This elevated temperature affects the insulation of the conductors, potentially leading to premature degradation and failure if not properly addressed. To mitigate this risk, the National Electrical Code, or NEC, mandates that the ampacity of the conductors be derated based on the number of current-carrying conductors in the wireway. The derating factors are specified in NEC Table 310.15. D3. This table provides adjustment factors that must be applied to the base ampacity of the conductor, which is determined by its size and insulation type. For example, if there are 4 to 6 current-carrying conductors in the wireway, the ampacity of each conductor must be derated to 80% of its original value. If there are 7 to 9 conductors, the derating factor is 70%. For 10 to 20 conductors, it's 50%, and for 21 to 30 conductors, it drops to 45%. Finally, for 31 to 40 conductors, the ampacity must be reduced to 40% of its initial value. The ambient temperature also plays a significant role in ampacity derating. The base ampacity of a conductor is typically specified for a particular ambient temperature, usually 30 degrees Celsius or 86 degrees Fahrenheit. If the actual ambient temperature exceeds this value, further derating is required. NEC Table 310.15. V2. Provides correction factors for various insulation types and ambient temperatures. For instance, if you are using THHN conductors with a 90 degrees Celsius rating and the ambient temperature is 40 degrees Celsius, the correction factor is approximately 0.91. This means that you would multiply the derated ampacity from the conductor bundling by 0.91 to obtain the final allowable ampacity. The fill calculation is another important consideration when using wireways. The NEC specifies that the cross-sectional area of all conductors within a wireway cannot exceed 20% of the wireway's internal cross-sectional area. This limitation is in place to ensure adequate ventilation and to prevent overheating of the conductors. It is important to note that this 20% fill rule applies regardless of the number of current-carrying conductors. Even if the wireway contains fewer than 4 current-carrying conductors, but the total cross-sectional area of the conductors exceeds 20% of the wireway's area, derating is still required based on the number of conductors. When comparing wireways to individual conduits, one of the key differences is the way heat is dissipated. In individual conduits, the conductors are typically spaced further apart, allowing for better air circulation and heat dissipation. This means that conductors in individual conduits can operate at higher ampacities than conductors in wireways, without exceeding their temperature limits. As a result, smaller conductors can often be used in individual conduits for the same electrical load, compared to wireways. This can lead to cost savings and easier installation. However, wireways offer other advantages such as flexibility and ease of access. Wireways are often used in applications where frequent changes or additions to the wiring system are anticipated. They also provide a neat and organized way to route conductors, which can be beneficial for aesthetics and maintenance. To minimize the conductor size and cost in wireway installations, several strategies can be employed. Firstly, optimize the wireway layout to minimize the length of the conductor bundle. The longer the bundle, the more heat will be generated and the greater the need for derating. Secondly, use conductors with higher temperature ratings. For example, THHN conductors with a 90°C rating can handle higher temperatures than THHN conductors with a 75°C rating. This can reduce the amount of derating required. Thirdly, provide additional ventilation or cooling to the wireway. This can help to reduce the overall operating temperature and allow for higher ampacities. This might involve installing ventilation fans or using a wireway with a vented design. Let's look at the implications of using wireways and individual conduits for a specific example. Consider a scenario where you need to supply power to a 40 horsepower motor that draws 52 amps. Assuming an ambient temperature of 30°C and using THHN conductors with a 90°C rating, let's compare the conductor sizes required for a wireway and an individual conduit. For the wireway with more than 40 current carrying conductors, the ampacity must be derated to 40% of its original value, according to NEC Table 310.15. B3. To carry 52 amps after derating, you would need a conductor with a base ampacity of at least 130 amps, which is 52 divided by 0.4. According to NEC Table 310.16, a number 1 THHN conductor with a 90°C rating has an ampacity of 150 amps, which meets the requirement. However, if the wireway contained fewer conductors, for example, between 10 and 20, the derating factor would be 50%. In this case, you would need a conductor with a base ampacity of at least 104 amps, and a number 3 THHN conductor with a 90°C rating, which has an ampacity of 115 amps, would be sufficient. In contrast, for an individual conduit, the conductors are not bundled together, so no derating is required, assuming the conduit fill does not exceed 40% and there are not more than 3 current carrying conductors in the conduit. Therefore, a number 6 THHN conductor with a 90°C rating, which has an ampacity of 55 amps, would be adequate for carrying the 52 amp load. This example illustrates the significant difference in conductor sizes required for wireways and individual conduits. The larger conductor sizes required for wireways can increase the cost of the installation, especially for long runs. They can also make it more difficult to pull the conductors through the wireway. Therefore, it is important to carefully consider the trade-offs between the advantages of wireways, such as flexibility and ease of access, and the disadvantages, such as higher conductor costs. In conclusion, using wireways requires careful consideration of ampacity derating factors, including temperature and fill. While wireways offer several advantages, the need for larger conductors can increase the overall cost and complexity of the installation. By optimizing the wireway layout, using conductors with higher temperature ratings, and providing additional ventilation, it is possible to minimize the conductor size and cost. When comparing wireways to individual conduits, it is important to weigh the trade-offs between the advantages and disadvantages of each system to determine the most appropriate solution for the specific application. Always consult the latest edition of the National Electrical Code, or NEC, and local electrical codes for specific requirements and regulations regarding wireway installations. Consider consulting with a qualified electrical engineer to ensure that the wireway system is designed and installed in accordance with all applicable codes and standards. This will help to ensure the safety and reliability of the electrical system. Remember to consider the voltage drop in the circuit. Voltage drop is the decrease in voltage that occurs along a conductor due to its impedance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To calculate voltage drop, you can use the following formula: voltage drop equals 2 times K times R times D divided by Cm, where K is the constant for the conductor material, which is 12.9 ohms circular mils per foot for copper and 21.2 ohms circular mils per foot for aluminum. I is the current in amps, D is the one-way distance of the circuit in feet, and Cm is the circular mils area of the conductor. If the calculated voltage drop exceeds the recommended limits, you will need to increase the conductor size to reduce the voltage drop. Finally, consider the short circuit current rating, or SCCR, of the wireway and its component. The SCCR is the maximum amount of fault current that the wireway can safely withstand. It is important to ensure that the wireway and its components have an SCCR that is equal to or greater than the available fault current at the point of installation. This will help to prevent equipment damage and personal injury in the event of a short circuit. The available fault current can be determined by performing a short circuit study. This study should take into account the impedance of the utility power source, transformers, conductors, and other equipment in the electrical system. The SCCR of the wireway and its components can be found on the manufacturer's nameplate or in the product literature. If the available fault current exceeds the SCCR of the wireway, you will need to install overcurrent protective devices, such as fuses or circuit breakers, with an interrupting rating that is equal to or greater than the available fault current. In addition to the NEC and local electrical codes, there may be other applicable standards and regulations that apply to wireway installations. For example, if the wireway is installed in a hazardous location, such as a chemical plant or refinery, it must comply with the requirements of NEC Article 500 through 516. These articles specify the types of equipment and wiring methods that are permitted in hazardous locations. They also require that the equipment be properly labeled and certified for use in the specific hazardous location. It is important to be aware of all applicable standards and regulations before designing and installing a wireway system. Failure to comply with these requirements can result in fines, penalties, and potential safety hazards. Here are some additional tips for installing wireways. Firstly, use the correct tools and equipment. Use tools that are specifically designed for cutting, bending, and installing wireways. This will help to ensure that the wireway is installed properly and safely. Secondly, follow the manufacturer's instructions. Carefully read and follow the manufacturer's instructions for installing the wireway. This will help to ensure that the wireway is installed correctly and that it will perform as intended. Thirdly, inspect the wireway before installation. Before installing the wireway, carefully inspect it for any damage or defect. Do not install a wireway that is damaged or defective. Fourthly, support the wireway properly. Support the wireway at regular intervals, as specified by the manufacturer. This will help to prevent the wireway from sagging or becoming damaged. Fifthly, ground the wireway properly. Ground the wireway in accordance with the NEC and local electrical codes. This will help to protect against electrical shock in the event of a fault. Sixthly, label the wireway clearly. Label the wireway clearly with the voltage, current, and other relevant information. This will help to prevent confusion and errors during maintenance and troubleshooting. Seventhly, keep the wireway clean and dry. Keep the wireway clean and dry to prevent corrosion and other problems. Regularly inspect the wireway for any signs of damage or deterioration. Eighthly, do not overload the wireway. Do not overload the wireway with more conductors than it is designed to handle. This can cause overheating and potentially lead to a fire. Ninthly, do not modify the wireway without consulting the manufacturer. Do not modify the wireway without consulting the manufacturer. Modifications can void the warranty and potentially compromise the safety of the installation. 10thly, use qualified personnel. Only allow qualified personnel to install and maintain Wireway systems. This will help to ensure that the work is done safely and correctly. In summary, the correct calculation of Wireway ampacity, understanding derating factors, and careful installation practices are crucial for ensuring the safety and reliability of electrical systems using Wireways. Adhering to NEC guidelines, considering environmental factors, and utilizing appropriate tools and qualified personnel will contribute to a successful and compliant Wireway installation.